Okay, welcome everyone. We have Eric Badin. Did I pronounce that well? Eric Badin.
Yeah, that's good.
Very good. With us today. He's a part-time researcher at University of Cambridge, where he has done this work. And yeah, in the rest of his time, he is a part-time consultant, part-time entrepreneur, lots of things. And yeah, he has quite a strong record in Bayesian optimization. But this work is not going to be on Bayesian optimization, or partly it will go.
Yeah, I
We'll
mean, I
see.
guess like adjacent, but yeah, not on Basel.
Yeah.
Yeah.
Well, we're very excited to see his new work. Yeah, please, we go ahead.
All right. So thank you. Hi everyone. Yes, I'm gonna be talking about subspaces in latent variable models, and yeah, the motivation will be for optimization, so it's related in that way. And this is joint work together with Sam Henry, Carl Hendrik, that I think most of you know, and Alexander Sturr and Jarvis Marginantu at Boeing. And yeah, the presentation will largely be based on this recent paper that we're going to present at ICLR in April. So yeah, so we are interested in optimization of high-dimensional objects, and in particular, we were thinking about working with 3D designs of aircrafts or individual parts like wings and fuselages and things like that. And traditionally, these designs, they are represented by a parametric model in, for example, CAD software. And then you have the limitation that within these models that you can't typically, you can't move outside of this typically quite narrow parameter space that you define around a particular CAD model. And this in turn then would limit the design space and the potential for finding new interesting objects around, outside of this. So can we do better with generative models is our thinking. And generative models, they allows us to treat objects in a more raw format. So for example, can treat them as point clouds, meshes, voxels, etc., instead of the parameter set of a particular CAD model. And this allows us to expand the design space beyond these individual models, and then to train on a large model where you can pool data from different models, but also from other places. And we can then define an objective function, defined over this space that could guide our search. And we could use computational fluid dynamic simulations for the use case of searching for airplane points and stuff like that inside of our objective function. So it just be part of evaluating it for a particular mesh, let's say. But with this, we face several challenges. One of which is that the internal representations of these generative models, they typically have tens of thousands of intertwined degrees of freedom, any one of which could have low relevance for the objective function. And these CFD simulations, they are very expensive to evaluate, which naturally would restrict the numbers of evaluations that we can make. And we cannot typically differentiate through the simulation, which then can provide less information to the optimization algorithm. And this makes effective optimization difficult because the space is large, it's information sparse about our objective, and we have a limited budget to evaluate it. So our approach is that we'll use design examples, to determine relevant degrees of freedom that we have for this. So if you imagine, us having a few examples, let's say these 3 examples of meshes, and this is kind of a toy example, but we have 3 meshes. And we would like to be able to, convert them into some representation and let us define, a space of similar designs to this, where we can move inside of a 3-dimensional cube, let's say, or in some low-dimensional space where for each coordinate we have a valid object related to these 3 that we can pick, so we can control what degrees of freedom are relevant. And then have objective function defined over this, to let us evaluate and apply optimization to this. So this is what we'd like to do. And but how to do this was in this kind of models is unclear before this work. So in this talk, we'll first go through a brief introduction to diffusion models, which are popular class generative models, and I'm sure you're all familiar with, and how objects can be represented by latent variables. And then the challenge that I mentioned, that the space is large, it's information sparse about objective, and we have a limited budget. We mitigate this by operating on subspace of relevant variables. But then we are faced with the challenge that in the prior literature, manipulating the latents, so rather than sampling from a diffusion model, but manipulating in other ways, often led to poor generation results. And available operations on the latents were largely restricted to just interpolating between two of them, and you have to make quite strict restrictions, strict assumptions about them. And we will discuss, kind of why that was the case, was unclear, and then show that we can lift the restrictions to do what we want to do in our motivation. So diffusion models. So it's just kind of a brief introduction. So in essence, to train a diffusion model, you start by defining a simple corruption process. So typically, it's gradually adding noise to an image until only noise remains. And you can think of this as we start with an object, which is say x0, which could be this picture, and we have our noise process that has pushed that to some pure noise, which is xt as is end of this index. And this process, this corruption process, we can denote f here, and we can think of it as applying to the object x0, we're applying a corruption to the extent of t. So in the noise case, it would be how much noise you blend into the image, and eventually, at the end of the noise process, you want the corrupted object to follow the distribution P that you decide ahead of time. Let's say a Gaussian. And what you do during training is that you fit the network, and the loss function for a particular T, usually just like take the expectation of a T. But the important bit really for a particular T is that you're training on. You take samples from the data distribution. Typically, you just take samples uniformly from the data set, approximate like that. And then you independently from that draw samples from a corruption distribution, could be Gaussian noise. And then you fit the network on the corruptions themselves, given the corrupted version and the extent to which it was corrupted. And then you use this fitted model to be able to reverse the process. So you start by sampling from the noise distribution or the corruption distribution that you kind of anneal to, and then you just take reversal steps. And we refer to P of xt as the latent distribution. And it's often specified as Gaussian, and it's due to the closed form forward process that would then simplify training, as you can directly sample from the corruptions for a given T. But there are you can do diffusion using other models, other corruption processes as well. So a way you can view this as well is stochastic differential equations. Or see the diffusion as an SDE. And that view was introduced in this paper from 2021 by Song. And there you define your forward process as an SDE with some drift term and some diffusion term. And it's a common assumption that you let the diffusion term be independent of X. Doesn't have to be. You can have more general SDEs, but then it would be more terms involved. And it's typical also as well to pick dW to be Brownian motion as well to have Gaussian noise. And what's really cool is that from this result from the 80s that you have the reverse processing closed form available, and it just evolves terms from the forward process and the marginal density, the score of the marginal density over the data at that particular team. And actually this, so the fitting objective, you fitted a network to the corruptions. In a lot of cases, that correspond to, under a simple transformation, learning the corruption distribution in expectation correspond to learning this, the score of the marginal density. So you can then use kind of train it the same way and just plug this in, even if you, regardless kind of if you do it in continuous time or discrete time. And yeah, what's I think is very useful is that you can convert the STE, so now the reverse process, to an ODE instead, by pretty much dropping the diffusion term and centering this one term. And what's cool is that it has the same marginals on each side, so that you're sampling from the from the noise distribution still, and you get samples from the data distribution, your kind of complicated distribution that you're kind of annealing to. Those still match, but for any particular noise sample, have a deterministic map to the other side, given the ODE that you then solve. So you can do deterministic sampling with like deterministic generation, or you can see it as a bridge across that's consistent, like that is deterministic. And because it's an ODE, you can always just invert it as well. It's called, we're going to refer to it as inversion, where you just run the ODE in reverse. So for a known object x0, like that noise-free image, we can map that to a corresponding latent or a corresponding sample that would reproduce it if you would draw it backward, solve it backward. But it's under some assumptions that we're going to get to. But yeah, that's the general idea, that you can embed data in this. And deterministic generation and inversion is also possible in discrete time models, as pointed out. So just to summarize that, a sample xt, at the kind of diffusion side, or like the latent distribution side, is a representation of an object. Given an object, we can map it back and forth. And this allows us to work with objects in a latent space, which can be more convenient than the original object space because you can have much simpler structure, and you can decide what that how that distribution should look like.
Does it matter the horizon T?
The horizon T, no, not really.
How many steps of adding corruption?
Yeah, I mean it depends on because you would solve it with higher quality to have a larger budget solving the ODE, but like it's arbitrary kind of how long it is, because you define that together with your corruption process. As long as it's maintained that it becomes noise on the other side. But it's definitely an important hyperparameter to what the schedule is, that you have to kind of gradually go there. And they're like in the research on what is best kind of noise schedule and things like that. So it matters, but the scale of T doesn't matter as long as you parameterize everything appropriately. But the number of steps can certainly matter.
The ideal thing to do is to take tiny steps and run it for infinity. But
yeah, exactly.
But obviously you can't do that. So
yeah,
what choices you make is one of the things that you get to.
And you might use a more sophisticated solver, or the solver, to afford to take fewer steps and take them more cleverly and stuff like that. So it's but yeah, with infinite compute you can just take tiny steps and just take them, lint space kind of thing all the way. But but yeah, unlike so in the talk, we're just gonna assume that we. So this we have an object to latent mapping, right? But we can define this in other ways. So it can be via diffusion models, but it can also be via other latent variable models like normalizing flows, which there is something called flow matching, which is type of continuous normalizing flow that's now very competitive. You can use that. It's kind of related to diffusion models in the sense that it's kind of taking the trick of doing score matching, pretty much similar to across to continuous normalizing flows. And then variational autoencoders, which is also closely related to this. Like a diffusion model can be interpreted as multiple stacked, variational autoencoders. So yes, we're just going to assume in the scope of this talk that we, have some mapping that's been learned from samples, when we can be agnostic to the specific class. And we just refer to xt as the latent variable, or latent for short. And because we're gonna mainly stay on the side of the latent distribution here at capital T, so we can just drop the time index and say it's x. So as we've seen, a realization of the latent variable is a representational object. One can easily draw from the distribution and obtain an object. Here's an example of that. So here we have a diffusion model, stable diffusion 2.1. It's called this for popular image model. And here the latent distribution is standard Gaussian with 36,000 dimensions roughly. And you draw a sample and you get a pretty picture. And you can draw samples like this and you get pictures out. But what if you instead want to pick the x by a different process than sampling from P of x? So for example, by an optimization algorithm, that they should pick these latents directly. What criteria should x meet to be valid? Is it necessary enough that it has a high likelihood under the latent distribution, where you would imagine that around the latent distribution you would just within a set of high enough density, kind of like a bounding box, or actually it's not quadratic, so it's not square, but a bounding sphere. When you're staying within there, within some threshold of density, everything is fine, and outside is bad, and you just let the optimization algorithm pick latents from within that bounding box, or bounding sphere. Would that be sufficient? And it wouldn't, right? So because you have the setup where the likelihood is not a proxy for model support in this case, and we talk about why, but just to illustrate, if the left side we're taking a random sample, and on the right side we've taken the maximum likelihood vector in the latent space, it's taken the mode, which is on for this Gaussian latent distribution, it would just be the mean vector, so the zero vector, and that wouldn't give us anything sensible. And a way to think of this is that the highest likelihood vector x is an extreme outlier when d is large. We would have a much higher likelihood than any sample that you would see, if you would sample until end of time. And just another way of looking at that is that classic result is that the norm of a unit Gaussian vector follows the Shire distribution with d degrees of freedom. And this distribution concentrates around square root of d as d grows large. And the likelihood of having a norm, which zero vector does, of 0, would tend to 0. So for example, having a norm outside of 187 to 196, or 197 is in this case, is virtually impossible in practice, given that x would be from the latent distribution. And this property of norm preservation is well known to be important when you interpolate between two Gaussian latents. And just to set some terminology. So if let's say we take two samples from the latent distribution here, which we'll refer to as seed latents when we kind of combine them. So let's say we have two, and we then linearly interpolate between them, then you wouldn't get anything sensible as soon as you leave the endpoints. Because of this, the intermediates won't have this similar norms as the endpoints. And that's why people use spherical interpolation instead in this setting, and which is designed to maintain similar norms as the endpoints. So you're just interpolating on a sphere instead. And that works. But motivated by spherical interpolation not always working well on inversions. So when you've taken known objects and inverted them, and then you use them to interpolate, there's been new methods developed recently. So in 2024, it was proposed to add additional Gaussian noise to interpolants via the inversion. So you kind of gradually add noise. So you have to run this for each of the interpolation points, so in the inversion. And then you have this thing where you have to trade off quality to quality of the images or objects being produced, and the adherence to the seed. So how similar, how kind of informed they are by the endpoints. And another work advocates to use back propagation. So you identify kind of interpolation paths in between the latents, which has plausible norms, while along the path you have a high similarity of the vectors, like high cosine similarity, for example. But why are these methods necessary or potentially helpful? Is there a problem with spherical interpolation that that causes the need for this? And yeah, no, not really. So when we show that in paper that spherical interpolation works, you get the that's not where it breaks, but the seed latents might not always be valid. So your endpoints that you're interpolating, they might be wrong, because we can note that the inversions are ODE solutions that might not be perfect in various ways. So like they're subject to finite solving steps. You might have too small compute budget to get a good enough data representation, and they suffer from numerical imprecision that has to be sufficient, and your setup could contain bugs. And even if it would be perfect, it wouldn't necessarily yield a sample from the latent distribution if the object is not drawn from the data distribution. And this might be happening because maybe there was a pre-processing step that was missed, then that would happen instantly of the known object that you're doing the inversion for, or it might just be that the object is not similar enough to the data that the model has been trained on.
So, dumb question. So when you have your latent distribution, that's where you say where you're taking your sample from. I mean, in the limit, that would be like a pure noise Gaussian distribution.
Yeah.
Or it's somehow still informed by the data.
Yeah, I mean, like when you're solving,
it has to be biased somehow. So it cannot be pure Gaussian, right?
No, because like when you're doing the inversion, you're not just running the forward process, right? You actually you have the reverse process, and then you have the ODE of the reverse process involving the score of the module density. That is what you run when you do the inversion. So it involves the output of the neural network, right? And that has been trained on certain inputs, right? So if you would feed it in different inputs, you would not necessarily get the behavior that you want. You wouldn't necessarily get the path to where you want to end up.
Yeah, that makes sense. But then how do you make sure that the distribution of latents is within the data distribution?
And we're gonna talk about that. So yeah.
I've also got a question, which is probably dumb. So, can you demonstrate this by taking a data point from your data distribution? So it's from the bottom layer, it's from E of x 0.
Yeah.
Running the ODE process back to the latent space, and then running it in the reverse direction. You end up with the same image.
Yeah, exactly. So that's kind of typically what you do to see like, oh, does it work? But actually, that's not going to be enough. You can still violate some important assumptions, and that's we're gonna talk about that. But that's a good question.
Thanks.
Yeah. So because remember that the network at the last index, over the time index that we're training the network over, at the very last index, it will be trained exclusively on samples from the latent distribution. If you have set up the forward process correctly, at least up to kind of like float position kind of thing, should be close. And the network may have learned to rely on a number of characteristics of these samples. And yeah, these characteristics can be interpreted as statistics following associated sampling distribution. So, for example, we talked about the norm of a unique Gaussian vector follows a Shai distribution. If you can imagine if the norm has a lower likelihood than the Shai distribution, and the network happens to rely on the norm, things might break. That it's it doesn't look like the input pretty much. But clearly, though, the norm is not the only thing that matters. So just to illustrate on a simple example, and this is on a diffusion model and a flow matching model for images. They both have unit Gaussian latents. And you take a sample, you get a pretty picture. And then if you would rescale the latent such that it has the mode norm, the most likely norm on the like square root of d, most likely norm on the Chi distribution with the right degrees of freedom, it wouldn't matter much. Like you get pretty much the same. But if you take another vector, let's say a constant vector, and you make it have that norm, it's not gonna work. And you would say, oh yeah, but that wouldn't have maybe the right mean, doesn't have the right variance, and also it's quite a weird thing to have just the same values over and over again. There are various features pretty much that a realistic sample would adhere to, and you might want to like list them out, but yeah, it's a network which is a flexible function approximator that learn to extract such a low reliance on certain features. So those dependencies could be relatively complicated, and they could be different for each model. So like imagine if you would take a network where the first thing you would do in the network is to normalize the input, such that it has one norm something, then it wouldn't be dependent on the norm anymore. So there are some dependencies that we learned from samples. So we, instead of trying to list these and test them, we suggest to use, because there's a whole area for this, so we're supposed to use classic distribution testing on the inversions to test broad statistics. And yeah, so we're gonna get into your question as well. See, I think I kept some of the slides. So we convert through. So when we test it, we just convert this high-dimensional vector, which is in D, to DIID scalars. So you can typically do that depending on the form is. And so I'm not going to go through too much into this. I'm just going to kind of like skip over this results and then go to other things. But we find that the KS test works really well, in the setting large D, to assess the latents if they are good. And this KS test is very broad, and it considers the distribution of the largest absolute difference between the empirical and the cumulative theoretical CDF. Right. So you look at distribution of that, and you see if there is any, and you detect if there is an unlikely difference on that, and then you can detect quite minute differences because you have such a large set of these scalars. And we show that if you have, using this test, if you have unrealistically low p-values, so if these vectors are very unlikely, given that they are sampled from the latent distribution, that they are extremely unlikely to come from the latent distribution. If you have latents having that property, then if you interpolate using spherical interpolation, that's gonna affect their visual quality, even though they are perfectly reconstructing themselves, right? So imagine you take the seeds, you run the inversion, and you run it back, and you get perfectly valid images. If you still didn't have enough settings for them to have valid, like have good enough characteristics, like be looking enough like real samples, then the quality of the interpolants might be completely destroyed, which shows up as them having also poor characteristics for samples. So you can detect that already in the seed latents. And yeah, so we can see that here as an example where if you're assuming that you have reconstructing seeds with high p-value or realistic p-values that you would see by chance versus ones that have p-value of, let's say, 1 in 100 billion or things like that, then if you don't use them, if you improve your inversion procedure instead, you get rid of a lot of cases where you would just have very poor visual quality of those interpolants. Yeah.
So I mean, I guess when you're talking about like why you would get a sample which can reconstruct but wouldn't interpolate, maybe like let's say that your models learn the score perfectly.
Yeah.
But you've got some time step discretization error. your forward and reverse process is going to be exactly the same. So you'll start from your sample, you'll have some errors due to the time step discretization. So you'll end up at like a bad latent, something that's non-Gaussian. But it will still, the forward and reverse is going to be exactly the same. So,
yeah, exactly.
So you'll still end up back at your image if you then ran the reverse process from there. But this thing is not Gaussian.
Yeah, it's like in the beginning, it was very dependent on how it ended up there, and it just reverses that step trivially. Because, exactly, but then because it's kind of outside of the manifold of these Gaussian samples, when you interpolate, you end up in regions that you don't then recover from when you take your reversal steps. And yeah, so just the point here is that distribution testing could help you debug your inversions and avoid downstream problems that otherwise would have. Because yeah, you might need to use more steps, maybe a better solver for that budget to be able to take better steps, can contain bugs, and the data might mismatch the model. So, but yeah, now we will just assume that the seed latents are valid and focus on manipulating them. So now, assuming that we have access to k latents, we want to form linear combinations of them. And these in turn, we can use to define subspace projections, interpolations, and other things. And we'll first address the common case of Gaussian latents, and then we'll extend to some a little bit more general distributions. So let Y be a linear combination of k Gaussian random variables with some mean and variance. And that is the latent distribution they're drawn from. Then Y is also a Gaussian random variable with just a different mean and covariance, depending on what the particular linear combination weights were at that place. And Y would only be drawn from the latent distribution and if 1 and 2 is true. And for linear interpolation, this is only met at the endpoints, which consistent Y doesn't work anywhere else. And for spherical interpolation, it's met everywhere if the mean is 0 and D is very large, which typically is, and it's consistent with it working well in those cases. So, and we are interested in linear combinations in general. So it should work for any W and any model, really, also like low dimensional things like that. Small dimensional models. So we will define just a simple transport map to a corrected variable Z for each respective Y. So it's a simple transform, which to ensure that each Z is drawn from the latents, which will substitute for Y. And let me show quite simply show that the transport map is Monnier optimal, meaning that it minimizes the quadratic plus line distance between this original distribution, of Y and the Z that we replace it to for that particular W. Because there is a map for W.
So why is it only interpolation? I mean, if you assume linear combinations, that means that probably you should be able to extrapolate well as well.
How do you mean?
Extrapolate beyond the examples. Can you do that?
Yeah, you can. Yeah. And yeah, some examples of linear combinations. So here we have interpolations, of course, and we might want to have centroids, but we're interested in subspace projections. And so let's say we have these k latents. So k samples drawn from the latent distribution, which might be, our objects or meshes that we have run the conversion process to embed in the latent space. And if we've done that well, they should have the characteristics of samples from the latent distribution. So we have them, and we stack them together to form X. And then if we use, for example, QR decomposition, we can get a semi-orthonormal matrix U from X. And we can then U transpose. We have a projection matrix that brings an X to the subspace spanned by our latents, which we can write equivalently as just UH, where H is just indexing the degrees of freedom that we have, the K degrees of freedoms, indexing that subspace. And the weights we can get by the pseudo inverse of x times the subspace projection, which we can then write. So we can get b as a function of h, and this allows us to pick projections directly by picking. So we can by directly picking h and compute the corresponding projections y that would lead to those edges, and then use the transform to the latent space for the given w to get z that would feed through the model to generate.
Sorry, can you?
Yeah.
Go back.
What's your?
Okay.
Oh yeah, it was quite quick.
Yeah. That's okay.
Yeah, feel free to stop me for any questions. Yeah, so here we are showing you have 5 examples. We have 5 images corresponding to 5 latents. We form a 5-dimensional subspace. And here we show a slice of that subspace and centered on X1, so the first one. And so use a grid over that slice. And on the left side, we show the kind of corrected latents and the generations from them. And on the right side, we show the uncorrected versions, which just, doesn't give you anything sensible because it's not from the latent distribution. And here's another example. Here's the same, also flow matching model, same stable diffusion tree. Just two working slices for 2 different pairs of dimensions. And of course, you can use slice any direction that you would like. And now we're back to this example, which was this is an experiment made by Sam, and they made a plot. And it's yes, he's just doing the same thing. So it's like we have these meshes. We did the same procedure from the subspace, and then we evaluated using OpenBSD, running the as a CFD simulation to get wave drag estimated for each of the designs over a then much denser grid. So you see the corresponding black points here. That corresponds to the designs we show, but we just ran it here 100 times 100 to get a surface out of the of the wave drag across this slice of the latent space or the subspace.
Well, the increase in the ambient temperature of this diffuse lab by a couple of degrees.
Yeah. Yeah, and the model is point cloud model, but then with mesh reconstruction, you get the meshes. And yeah, the model we use there is slide, and it's trained on ShapeNet. So it's just like on all kinds of shapes kind of thing. So yeah, containing more than planes. And it's, yeah, kind of like a toy example. Okay, so I'll start and then just talk briefly about general distributions. So yeah, Gaussian latents, they're common, but they're not always appropriate depending on the model. So many models, they use other distributions. In particular, there might be some elements where you have some constraints. You want it to be positive and things like that, and you pick different other distributions to use. But it's very common still because you can pick what the distribution is, that you have independent components, so that the elements are all independent in the latent distribution. And we will now just address forming linear combinations for such distributions. So if we let Phi be a distribution with independent components across elements, and we know the CFD and the inverse for each individual distribution for any given element, which could be different, then if we're given weights then to form a linear combination, and we have the seeds that we want to combine, we have all of the x's, they are drawn from P. Then we propose a transport map now is defined per element because they're all independent. And that looks like this. And it's quite simple really. So I start from the right side to show that. It's like if you start with xkd, that would be one of the seeds and one of their dimensions, one of the elements. It follows that distribution with CFD phi d. If we map that variable via the CFD, then this would just be a uniform variable between 0 and 1. And if we push that through the inverse CFD of a standard Gaussian, we are going to get a standard Gaussian sample. So we then have, for that particular seed, that particular dimension, we have then this epsilon kd. And then we form a linear combination of these seeds for that dimension. And we just use the map, so the transform from before, which maps this to one standard Gaussian variable. And then we can just do the thing in inverse. So use the CFD of the Gaussian to map it to a Gaussian variable, and then to a uniform variable, and take the uniform variable and bring it back to the original distribution. And this map is also Monge optimal, and it just follows from that pretty much the definition of optimality for that in the scalar case, by just using the CFD and the inverse for that distribution. So to map it across. So in conclusion, latent variable models such as diffusion models are powerful to represent objects. The latents need sample characteristics, but we can test this to debug the inversions, for example, or other procedures that creates latents that are not explicitly sampled. And we can navigate the space of objects by manipulating these corresponding latents. And we've introduced a very, very simple but general method for linear combinations, which allows subspace projections and other operations, whilst importantly, it allows us to stay on the manifold, so that when you're querying it using optimization, you get points that are valid. And this in turn allows optimization methods to operate on these objects. And in future work or current work, we want to do actual optimization on this. With this, that's what we're doing. And now, happily, working with Sam on this as well. It started in the autumn. Thank you for listening.
So maybe as an opening question to optimization. So now you've got a way to navigate through your space and getting relevant images. Do you have a notion of proximity, which I guess you do? Proximity to some, you call them seeds.
Oh, okay. So
like, can you get close to one or far away from one and close to another? And
in between, yeah.
In between, even if it's not like Euclidean distance.
No, yeah. Like typically we use an inner product, like cosine similarity between things. But like if you're in the low-dimensional subspace, then you can use, other things would make sense as well. Like you could use Euclidean distance if you are, on that projection. Yeah, and what would be best? I think it's depends. But yeah, there's.
So my question is, technically, how do you get your dissimilarity? Is it, or maybe we could go back to the projection definition. You have this H, which I think contains, like, would define the similarity, maybe. Or maybe I got that wrong. Yeah, this slide.
Yep. So.
I mean, if you do linear interpolation, simple one, forget everything. You just look at your weight. If your weight is large, you're close to this point and far away from that point. And then you can choose how far away you are from each. And if you choose 0.5, you're exactly in the middle.
Yeah, exactly.
So here you're doing something sort of similar.
Yeah, you're just doing it in like you basically are parameterizing in that way, and then you're just doing a transformation of that.
So I guess it's how you got your grid of interpolation.
Yeah, exactly.
So you just sample W's
as
a regular grid.
Yeah, you just do linear interpolation, and then you just project the linear interpolation into like this space.
So you can either like parameterize in terms of the W's, in terms of the ages, age there, or the original X's, then which you would then map into this space. So you can do it in different ways. But yeah, exactly. You can have a distance over just the W vectors instead of.
Yes. Once you have a distance, you can do your explore exploit.
Yeah,
exactly.
Which is
Yeah.
that's what we need.
I think it is normally, or from what I've seen. I guess maybe this doesn't apply in optimization, but certainly when you're doing like grids, it's like if you parameterize in terms of W, then you basically are saying it's like how much of each example do you want in. So all your axes are like kind of 0 to 1. If you parameterize in terms of H, then you kind of remove anything that's like you have this orthogonality, so you kind of like remove all the contribution. Like you pick one. The first example is like 0 to 1, and then the next one is like all the variation that can't be explained by that one. But then the scale of that is like it could be, if it's 99% correlated, then you have massively different scales in your axes.
Because they can be quite important because because if you're picking your examples X, they might be very, very similar, right? And then they could be far from being orthogonal to each other. And that's this all. Yeah. So H is in a space where the basis vectors don't correspond to the X's, but there is of course a map between them.
Yeah.
And that's why you're using this very inverse of X to just bring them back into that coordinate system in terms of the latents instead.
Yeah.
Could you explain maybe a bit more the grids you showed? I'm not sure.
Yeah, definitely.
What they meant exactly.
Yeah. So because we have five latents, we have 5 degrees of freedom basically, because everything is expressed in terms of those vectors. So we have K is 5 in that case. So you have this 5-dimensional subspace, and this is just showing on the left side a slice across there. Now it's an axis aligned slice, and I center it such that X1 is in the middle. So, and this is gridded, right? So like if you would continue zooming in, then it should be pretty smooth, like a gradual change from any one of these calls to the other. But it's smooth, but it might not be. It could be sudden changes, because like you can just imagine that there is some surface where things are going maybe up and down, things like that, and you just grid that, and that's what you're looking at here. So you see some smooth structure, but not always. It can seem like there's a big jump here, but there should be, if you would continue gridding in between these two, that you would see a smooth change between them. And like
this is a slice. So you said X1 is in the center. So you go from X1, you go axis aligned. So you're moving from X1 towards X3 or something. I'm sorry.
Yeah, you might not see X2 and X3, etc. in this particular slice. You would know that all of these 5, they lie within the subspace. They're gonna have some coordinate. You could set it up so that they are the corners and things like that. That's not how it is here. They're somewhere in this space. X1 we see in the middle, because that's the slice I'm at. The problem is like the X4 is probably fine somewhere relatively close to X4 here. But it might be a little bit further in some direction.
I mean, if you go to the plane one, it's pretty straightforward. So like the bottom left corner is like
X1,
X1. Right? The top left corner is like it's 70% X2. It's like basically everything's got 0.3 of X1 in it.
Mm-hmm.
And then if you go up, you add more contribution of X2. And if you go right, you add more contribution of X3.
So because you parameters in terms of W's, right?
Yeah, I parameterize in terms of W's. So like So like it's literally like the right bottom right corner is like 70% x3 and 30% x1 or something.
Yeah, that one's really clear.
Yeah.
I'm not sure, but is the other one the same thing?
I think
Yeah.
it's slightly different parameterization.
Okay, it's different parameterization, so you don't go from
Yeah.
x1 to
Yeah.
x.
So like,
You go into a latent space.
yeah, I think like, so yeah, these x1s, x1 to 5, they're just used to define the space. Like kind of their features are pretty much like defining the space, but then the only one we see is one of them, but they are somewhere in this cube. And a lot of things are similar to them. They form a coordinate system. Yeah, so that's just the idea with them. Not that we should see them in the picture or anything.
Are all of them, like in this example, are they all like proper cars, or can it just be like something in between two pictures that doesn't end up to be on the side? It's just
Yeah, it's a good question. So actually, this is conditional generation. So like everything that this model is going to produce is going to be cars
okay.
because they're using a prompt. But then, so if you say, for example, a sports car that looks like this, right?
Yeah.
It would, if the model is doing what it should, you would always get samples for any latent producing that. But all the remaining variations, all the ways of expressing that, the angle, there might be details you haven't expressed.
Yeah.
That's all going to be encoded in the latent space, and that is what you are, moving around within. So, like in some models, you have you can do prompting, you can do like add additional conditional information. Given all that extra information, is just a new diffusion model.
Mm.
It's just like you can see it as unconditional given that. It's just, and everything that it can express is encoded in these variables that you're moving around.
Okay.
So it's easy to combine with other things in that sense. You're just forming a new model basically when you do conditioning. It's like, oh, I want this to be cars. Here we said I want it to be shares.
Yeah.
And you get the same effect, but like you used describing the remaining variation basically.
Any question?
I wanted to just back to the transformation. That you're doing. So I don't think I quite got this. So, like a linear interpolation would be kind of like just a direct linear interpolation between two sort of like vectors in the latent space, right? Like draw a line between them somewhere along that line. Then spherical would be kind of like, would that be sort of like rotating the vector into the other vector kind of thing? Is that?
Yeah, and we can look at but yeah, like exactly. And like now we don't use spherical interpolation and stuff like that because we don't need to because of the map. We don't have to assume it's Gaussian either. But like as long as you do the corresponding map. But like exactly, like in spherical interpolation, you're using sine function to implement just the behavior that you're moving on the surface of a sphere.
Okay. Yeah.
And that's to have around zero. So that's why you have similar norms to the endpoints.
Yeah, sure. And then, sorry, I think I got a bit lost here. And then the type of interpolation that you were kind of proposing, what was happening there? So like a geometric interpretation, I guess, is what I'm trying to get my head
So
around.
actually, in the Gaussian case for the interpolation, it's very similar to spherical interpolation. It's like spherical interpolation is a close approximation. If D is large enough, it's a close approximation to doing this.
Okay, that makes sense.
So yeah, so like it's just basically saying that we can do, a little bit more, we can do more than interpolation in that case, because then you have to stay on a sphere, generalizing spherical interpolation to more using more seed vectors and other operations. It's not trivial.
Okay, yeah.
So we can skip that, right? Because it's just kind of mimicking this thing of getting a similar norm, but we can directly control for that. That's kind of the idea.
Okay, okay, yeah, I think that makes
And
sense.
in the Gaussian case, it's mainly basically the norm, but you have to make sure for each projection that it is maintained.
Yeah.
But yeah, you can do it for all kinds of operations. As long as, like for us, yeah, linear combinations, and yeah, and other distributions.
Cool.
So for the optimization, basically the idea is you have to impose some kind of evaluation function of these generated objects, and then you just do whatever optimizer you want over the space of W's to maximize that objective. That's the core.
Yeah, exactly. Space W's or spatial ages, whatever is easier for your particular problem. But yeah. Exactly. So you can pick the dimensionality and you can pick the kind of degrees of freedom. But it also assumes that you have a good generative model to begin with, right? If you're like intermediates and not, we need a model that would, all the solutions would have to be part of the subspace that you're defining, right? So you would have to make sure that you have a good model that has interesting solutions.
Yeah.
Time?
Yeah, we're in time. Well, thank you, Eric. It was a very interesting talk.
Welcome. Nice to be here.